Today we will be explaining what the Kaplan Meier curve is, and we are the group Stats What She Said. To start off, the Kaplan Meier curve is a type of survival time analysis in which the curve graphically represents the survival rate. The survival rate depicted in a graph is able to give you a probability of an event occurring over a specific time period. There are two types of variables, which include time on the x-axis and survival rate or probability on the y-axis. One example of survival analysis is the time period when a person goes to the dentist for a filling until the filling ends up breaking. Based on the graph on the right, it is clear that a curve can be created because as more time passes, their survival rate would decrease. When you want to know the survival rate after so many years, you look for the corresponding y value. Then you are able to interpret what the curve means.
Let's go through an example of how to create a Kaplan Meier curve. We start with data that shows when each subject dies. We then make a new column with all the time points where a death occurred and add a row 0. We then make an M column where we list the number of deaths at each time point. For example, at time 7, there were 2 deaths. Next, we make an N column, which is the number of subjects that made it to a time point, including those who die at that time point. For example, a total of 10 people made it to time 3, including 1 person who died there, and 9 people survived to time 4, including 2 who died there. By dividing n by the total number of subjects, we get our survival rate, which when plotted gives us our Kaplan Meier curve. To interpret these curves, we need to remember that steeper curves mean lower survival rate, and flatter curves mean higher survival rate. In the chart, we can see Group 1 has a higher survival rate than Group 2. Flat areas represent periods of stable survival.
Censored data is a necessary complication of Kaplan Meier curves due to the simple fact that studies cannot continue indefinitely and participant follow-ups aren't perfect. Sometimes, participants choose to leave the study, or the study ends before they experience the end event, and thus the researchers do not have the second data point for this participant. This is important because the researchers do not know when the end event occurred or would have occurred, which means they don't know when to mark this end time on the graph. It is data in itself, albeit incomplete, that the participants had survived that long before leaving the study because they had not yet experienced the event of interest at their most recent checkup. Instead of removing the individual's data entirely, the researchers mark the time when the participant dropped out or was removed, and this is called censoring, specifically right censoring. Censored data is plotted on the graph as a hash mark at the time point in which the data was censored, typically when the participant dropped out of the study. Kaplan Meier curves with a lot of censoring indicates a problem in the study design or suggests that the treatment was so ineffective that participants leave to pursue other options. On the other hand, no censoring at all could mean that the researchers excluded that one-sided participant data altogether. Returning to the tooth filling example, several participants of this study were censored, including someone who moved away and could no longer participate due to distance. One participant lost their entire tooth, which fails to provide accurate data about their survival of the filling, and one participant died. Another participant simply did not experience their event before the conclusion of the study.
There are a few assumptions made with Kaplan Meier curves. The first assumption is random or non-informative censoring. This means that the occurrence of censoring is unrelated to the likelihood of experiencing the event of interest. Censoring should be random, not influenced by factors that may affect the event outcome. If censoring is not random, the estimated survival probabilities may be biased. Second, there must be independence of censoring. The occurrence or timing of censoring for one participant should not provide any information about the censoring times for other participants. Third, the survival probabilities estimated at each time point must remain constant over time. If there are time-varying factors or time-varying treatments that can influence survival probabilities, this assumption may not be valid. Finally, it's assumed that there are no competing risks. The Kaplan Meier curve assumes that the event of interest is the only possible outcome, and that there are no other competing events that could prevent the occurrence of that event from being studied, such as causes of death.
So let's say we're interested in comparing two Kaplan Meier curves about lung cancer deaths in smokers and non-smokers. Visually, the curves look different, but how do we test if that difference is statistically significant? We would use the log rank test. This test uses the null hypothesis that there is no difference in the survival distributions, and the alternative hypothesis states there is one. This is similar to a chi-squared test where we attain a test statistic based on the observed survival versus expected survival, and we then calculate a p-value. If p is less than 0.05, the difference between the two distributions is significant. For this to work, there are several assumptions that must be met. The survival of individuals in each group should be independent of one another. Censoring should not be related to the event being studied or group assignment. and the hazard risk must remain proportional. So for each individual in a group, it should be constant for that group over time. Going back to the smoking example, assuming all conditions are met, the log rank test has had a p equal to 0.034, demonstrating there's a significant difference between the two distributions, that smoking significantly lowers survival.